Hello, guys. Today you're going to learn about some important petrophysical terminologies that are needed for formation evaluation. So, before learning about different well logging tools, just let's review these terminologies. Porosity is one of the most important parameters in petrophysics, and it is a measure of the volume of pores over the total volume of rock. So when we say the porosity is 30%, that means that about 30% of the rock volume belongs to pores. And why it is important? Because it is directly linked to the reservoir economy. So a reservoir with higher porosity has more ability to store oil and gas. And and that's something that we have to consider when we want to have some evaluation about the revenue that we may make from a hydrocarbon reservoir. Okay. It is possible that, for example, we have a reservoir with high porosity, but the reservoir is small. But because the porosity is high, the reservoir has a lot of oil and gas. We can make enough revenue from that reservoir, so it cover the cost of mm, production, and also it makes some benefit, makes some money for the investor. Now, just let me ask you another question, and it's still like tricky question that I ask my students. And assume that we have two rock models, rock model A and rock model B. And just let me make an important assumption here. So we assume here that the grain in each model, rock model, almost the grains have the same size. For example, if we measure the size of this grain is almost equal to this grain. And the same for this the rock model B. So for example, if we measure the grain size here, then we're going to notice that, okay, it is almost equal to the grain size here. Now, having said that, which of the following rock model has higher porosity? This is the question. Okay, just I'm going to give you a few seconds to think about it. Okay, guys. Many times, I've noticed that most of the students answer that rock model B should have greater porosity, and the reason because they say that, okay, we have bigger pore space here. I've just selected an area of rock model A, and just let me count the number of pores that we have here. We have 1, 2, 3, 4, 5, 6, 7. If I choose the equivalent area within rock model B, okay, and if just I want to count the number of pores that we have, just let me how many pores I'm gonna have in rock model B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. So as you see here, although the pores in rock model B are much smaller, but we have much higher number of pores in rock model B. And as a result, I can make the conclusion that the both rock models should have the same porosity. Okay, so one of them has much bigger pores, but a fewer number of pores. The other has a smaller pore size, but higher number of pores. And indeed, that's the question. So both models should have the same porosity. And the reason, because the porosity doesn't depend on grain size. So what I mean, if it is possible that you have like two different rock samples, one of them is composed of a small grain, the other is composed of larger grain, but they may have the same porosity. Indeed, porosity depends on how grains are well sorted. Okay. What I mean, if the grains in rock almost have the same size, we say it very well sorted. In that case, the rock will have high porosity. On the other hand, if we have a rock in which the pores are poorly sorted, which means that we have a wide range of grain size from very small to big, what you see here, in that case, the rock has very low porosity. So indeed, the porosity doesn't depend on grain size, but depend on grain size distribution. So the wider range of grain size distribution that we have in a rock, the rock will have lower porosity. Another important definition of porosity is the effective porosity, and the effective porosity is the porosity of those pores that contribute to the fluid flow. Okay, so for example, the porosity that is not considered effective porosity include includes water-bound to clay particle. So clay particles, there is a strong attraction between the water molecules and clay particles. And because of that, if the water molecules are bound to clay, they cannot move. So it is another one example of the porosity that's not considered as effective porosity. Another example is the porosity of the isolated pores. So if we have a like pore in a rock that is not interconnected to other pores, uh, again, this is another example that that pore cannot contribute to fluid flow. So we may call it the isolated pores or isolated Weige or we may call it the Weige porosity or wax for this example. Uh, the effective porosity is important because it is linked to the permeability, and the permeability is the ability of rock to pass the fluid. Okay, so just let me give you an example. So assume that we have a piece of glass and we place a drop of water on the glass. What we see that the drop of water will not penetrate the glass, and the reason because the glass is not permeable. If we repeat the same experiment but a piece of paper, we're going to see that the water will penetrate the paper, and because the paper is permeable. Again, permeability is important because we are not able to produce oil and gas from a reservoir unless the reservoir is permeable. And the more permeable the reservoir is, it means that we're going to have a better production. The SI unit that we use for permeability is a square meter, but indeed in oil and gas and also other fields such as hydrology and fluid dynamics, we usually use Darcy. 1 Darcy is equal to 10 to the power of 12 a square meter. But the more common, I can say, a unit that we use in oil and gas is millidarcy. So, for example, we say that the permeability of this reservoir is 1,000 millidarcy, 10 millidarcy, and etc. What you see in this table shows the permeability with respect to the grain size, the state of consolidation, and fractures. What you see here, for example, for gravel that is composed of larger grains, if the rock in particular is not consolidated, is unconsolidated, we're going to see the rock should have very, very high permeability, about 10 to the power of 8 millidarcy. On the other hand, we notice that, for example, for very fine sand, again, assume that that sand is not consolidated, the permeability is much smaller. For example, it may varies from 100 to 1 millidarcy. The finest particle belongs to clay, and if we have unweathered clay, in that case, the the permeability may varies from 0.1 to 0.0001 millidarcy. In that range, we may consider the clay to be impermeable. So what you notice here, the rock with larger grains have higher permeability, in particular if the rock is not consolidated. Now consider another rock type, and that is about consolidated rock. Generally speaking, consolidated rocks usually have lower permeability. For example, fresh granite, as you see here, has extremely low permeability that we can consider the rock to be impermeable as something that, although the rock maybe is is composed of uh, fine grain, and if it is consolidated, still if it has some fractures, the fracture will help to improve the permeability. So just if I want to summarize what we learned from this table says that if we have a rock that is composed of larger grains, it should have higher permeability. Another factor is consolidation. Unconsolidated rocks usually have higher permeability. And another is fracture. Fracture rock usually have higher permeability. So what you see here, it is like graphical sketch of what I mentioned in the previous slide. As you see, gravel has higher permeability compared to fine sand and compared to clay. Okay, so guys, this plot is very interesting, and because many petrophysicists try to see if they can link uh, permeability to porosity. So what they did, they collected different rock samples, they measured their permeabilities and porosities, and they plot them versus each other. And what they found that the correlation is not as strong. So for example, here you may see it is possible that, for example, a rock has very high porosity. For example, what you see here that I highlighted, about 30%, but it has very low permeability. On the other hand, it is possible that the porosity is low, for example, what you see here, but the permeability is high. So the reason, because the permeability is mostly related to how pores are connected to each other, okay? And the porosity is the measure of the volume of the pores. So if the rock has a lot of pores, but those pores are not interconnected with each other, in that case, the rock will have uh, low permeability. Another thing that we may notice, rocks with smaller grains have lower permeability, but again, that rock may have high porosity because those grains are well sorted. So that's the thing that you should notice, that maybe in general, we can say that we should expect that when the porosity increases, the permeability increases, but it's not the case. The correlation is not that strong. So here, just let me pose another question, and this is, why do rocks with larger grains have higher permeability? So here is my question. In order to answer this question, just let me introduce another concept that is tortuosity. That is a property of curve being tortuous, and it is defined by L over X. Here, X is the length of a rock sample, and L is the root of flow. Okay, and it is obvious that the minimum value for tortuosity is 1, and that happens when L is equal to X. And that will yield the maximum permeability. And the higher value that we have for tortuosity, it means that the permeability is lower. Now consider this rock sample. As you see, grains are not symmetrical, and the major axis of grains are along a direction. Now consider two different flow directions, one of them along B, the other along A. Now just let me ask you this question: which direction provides a better permeability? Okay, so the answer is A. And the reason, because along A, the tortuosity is lower. Just let me draw a flow route along a direction. As you see, it's almost close to 1. I mean, the tortuosity is almost close to 1. And just let me draw the flow route along B direction. If just I want to draw it right here, it is obvious that along A direction, the tortuosity is lower. And for that reason, I can say that along A, we're going to have lower permeability. Another important concept is irreducible water saturation. That is the lowest possible water saturation that we may achieve for a given reservoir rock. So just let me explain the concept. As I mentioned, the water saturation cannot be um, zero because always there is a strong attraction between the water molecule and a smaller pores, as we may term it as capillary pressure. And how it works, it is that assume that we have a reservoir rock in the beginning. And in the beginning, the reservoir rock is 100% saturated by water. And then oil and gas migrate from the source rock to the reservoir rock, and hydrocarbon displaces the water. Okay. So the hydrocarbon cannot displace all the water. It can displace a fraction of the water. And so the more hydrocarbon that is injected into the reservoir rock, the more water can be displaced. But it reaches a minimum value that we may call it irreducible water saturation. Another related term is connate water saturation. Connate water is the lowest water saturation that we observe in a reservoir. So maybe you may consider irreducible water saturation is the theoretical lowest water saturation that we may achieve in the lab. But connate water saturation is the lowest value that we see in a reservoir, we observe in a reservoir. And from that point, you may notice that the SW that we see, we may calculate in our calculation should be always, okay, bigger than SWI or equal. So if you, in your calculation, for example, in well logging, you calculate the water saturation is 0, it means that you have done something right. SW is always non-zeros. Always we have some water saturation in the reservoir. Doesn't matter if the hydrocarbon is purely oil or is purely gas. Another interesting definition is a specific surface area, and that is defined as the area over mass. Or it is possible that we may consider the area over volume. Okay. So either of these definition, we may call it a specific surface area. And what you see here, so again, don't forget, we measure area and divide it over volume, and we call it a specific surface area. What you see here, it shows the specific surface area here for different objects. And as you see, for example, for a sphere, it is equal to 1 over A, and A is the radius of the sphere. What you may notice here, the smaller sphere that we have, this smaller radius, we're going to have larger specific surface area. So now just let me ask you a question, is that consider two porous medium, A and B, and A has a greater specific surface area than B. So here is the question. What do you think in terms of the permeability? So which one should have higher permeability? So the answer is indeed B. And the reason, because higher specific surface area means that the grains should be smaller for this rock type. So A has a smaller grain compared to B, and we know that the smaller grains means lower uh, permeability. For that reason, I can say that uh, B should have higher permeability compared to A. So look at the grains that we mentioned before, sediments, and we know that clays are the finest sediments that we find in nature, and for that reason, we can say that clays should have very high surface area. In addition, there is a strong attraction between the clay molecule, clay minerals, and water molecule, and as a result, uh, if we have some clay in the formation, due to its high specific surface area, the clay is not permeable, and it can absorb a huge volume of the water, and thus clog some pores and reduce the entire permeability of the reservoir. So in particular, if we have clay and the configuration of the clay is that the clay minerals are dispersed within the pores, that clay can significantly reduce the permeability and something that we should. Okay, now just let me talk about some important definitions in terms of resistivity. So one of the most important resistivity is RW. That is the electrical resistivity of the water in the formation. Okay, so in deep reservoir that mostly we deal with in oil and gas, the formation water is brine, so it means that there are a lot of sodium chloride ions in it, and for that reason, the brine is conductive. So RW usually is a small number. Then we have R0 here, that is the resistivity of the reservoir rock when it is 100% saturated by water. Here, O or zero doesn't mean oil. Maybe if we want to memorize it better, consider that zero means that 0% of hydrocarbon saturation. So when we say R0, it means that a reservoir rock that has zero, or a rock that has zero hydrocarbon saturation and 100% saturated by water. And so when we talk about the rock is composed of like two-part grains that are not conductive and the fluid that is conductive. And as a result, if we compare these two resistivities, R0 always is greater than RW. And then another definition is the formation factor that is given by R0 over RW. And because R0 is greater than RW, formation factor should be always greater than 1. So why formation factor is important? Because formation factor is linked to porosity using this equation. And here phi is the porosity and m is cementation exponent. And it has been reported that for most of porous rock or sedimentary rock, it has an average value of 2. And these are the two famous equations that we may see. So if the reservoir rock is carbonate rock, which means that it can be limestone or dolomite, which means that it can be limestone or dolomite. It is defined by F is equal to 1 over phi square. And if it is sandstone, it is equal to F is equal to 0.811 over phi square. So as we see here, it is very interesting that if we measure some values of the resistivity, we can link it to the porosity, that is a petrophysical property. Now just let me talk about another important resistivity, and that is RT. And RT is the resistivity of the formation rock. Okay. So if, for example, we deal with a formation that is 100% saturated by water, RT is the same as R0. Otherwise, for example, if the formation has some oil and gas saturation, RT should be greater than R0. So here I may ask you a question, and that is, why does an oil saturated rock have much higher resistivity than a water saturated rock? So here is the question. If the water saturation is not 100%, why RT is greater than R0? So the answer is that the oil and gas are not conductive. So a rock that has some hydrocarbon saturation should have higher resistivity. Now we're going to get to I can say that one of the most important equations in this course, and that is the first Archie's laws. And as you see here, the first Archie's law links the water saturation in the formation to RT, RW, and phi. So it says that if you are able to measure the resistivity of formation water, and if we measure the resistivity of the formation, and if we have some estimate of porosity, then we can estimate the water saturation in the formation, and from water saturation, we can estimate hydrocarbon saturation in the formation. And here is a C is constant. For sandstone, it has a value of 0.9, and for limestone or dolomite, I mean carbonate rocks, has the value of 5. So this equation is very important, and this is one of the two important equations that we deal with in this lecture, and in this course, and you should learn it and memorize it. Okay, guys. Previously, I mentioned that what happens, so if we have during drilling, we have the the mud pressure that is PM, and then in the reservoir, we have fluid pressure that is PF, and usually always PF is smaller than PM. And as a result, the mud tends to penetrate the formation. However, just the mud filtered or the either the mud filtered can be water for the oil-based drill mud or oil for the oil-based drill mud. That's called mud filtered. Penetrate the formation, and the mud is deposited over the borehole wall that is called mud cake. So when the mud cake becomes thick enough, it indeed acts as an impermeable layer and prevent further penetration of mud filtered into the reservoir. So here is something that is interesting here. Just notice that if for example, formation is not permeable, or for impermeable formation, we don't, there are not going to be any penetration of mud filtered into the reservoir. And that's the thing that mud cake forms only in the vicinity of permeable formation. And the thickness of the mud cake correlates with the reservoir permeability. So the higher permeable reservoir that we have, we should observe a thicker mud cake. So if we look at the reservoir borehole, we're going to see that the thickness of the borehole may vary something like that. So here, if the layer is impermeable, the reservoir diameter um, is higher, is larger, and when the layer becomes permeable, the borehole diameter becomes tighter. And that's the thing that whenever we want to, uh, you know, characterize the reservoir, one of the things that we should measure is the borehole diameter because it's directly linked to the permeability of the reservoir. And also for some correction, for example, some resistivity correction or gamma ray correction that you're going to see, we need to know the borehole diameter. So that's something that you just consider. The borehole diameter is not constant, although we drill the reservoir with the same bit. And depending on the permeability of different formations, the borehole diameter will change as a result of the thicknesses of the mud cakes. Okay, guys. So now in the area in the vicinity of the borehole can be divided into three zones. The first zone is called flush zone, the area that is very close to the borehole. And in the flush zone, all movable fluids have been displaced by the mud filterate. Okay, so the movable fluid can be the formation water that was initially in place and also a fraction of hydrocarbon. So in the flush zone, all the movable fluids have been displaced by the, the mud filterate. And then we have transition zone. Transition zone is the zone a little bit away from the borehole in which a fraction of movable fluids have been displaced by the mud filterate. And then we have virgin zone area away from the borehole in which no fluid has been displaced. And here, another important property that is invasion diameter is the diameter of both transition zone and flush zone. And why it is important? Because again, it is linked to the permeability of the reservoir. The more permeable that the reservoir is, we have higher invasion zone. And that's the thing. If we can measure it, we are able to have some idea about the permeability of the reservoir. Now, just let me talk about some important resistivities. One of the resistivities that may be important is the resistivity of the real mud. We show it by Rm. And the reason why it is important, because sometimes, in particular, when we measure the resistivity of the reservoir, it may be important. If it is too conductive, we may use different logging tool for resistivity. And also the resistivity of the mud cake can be important because there are some methods that measure the thickness of the mud cake by measuring RMC, that the electrical resistivity of mud cake. Now, another important resistivity is RMF, that is indeed the resistivity of the mud filterate here in the flush zone. Okay, just notice that the mud filterate here in the flush zone, sorry, just let me write it here. The mud filterate is in the flush zone, we call it with RMF, and you may consider the equivalent in the virgin zone is RW. Okay, so RMF is the electrical resistivity of the water or mud filterate in the flush zone, and RXO is the resistivity of the formation, okay, in the flush zone. Okay, just let me say something. RMF versus RW. And here we have RXO, that is related to the rock resistivity, versus RT. At the same time, you see that SXO is the water saturation in the flush zone. Okay, so here, SW is the water saturation in the virgin zone. But here for the fly zone, we call it SS, SXO. So again, SXO here is water saturation versus SW. So again, as you see here, for well logging, not only we for reservoir, I can say for reservoir uh, evaluation or formation evaluation, not only we care about SW, but also we should care about SXO. And the reason why SXO is important because SXO gives us some idea about the volume of the producible oil from the reservoir. Okay. So in other words, a rough and inaccurate estimate of the volume of the oil that we may produce from the reservoir is given by this equation. So if just I want to more or better explain this equation, I mentioned before that we are not able to produce 100% of oil and gas from the reservoir. We may produce a fraction of it. We may produce 10% of the oil in the reservoir, 20, 30, and more. But we are not able to produce 100% of the oil in the reservoir, and that is called recovery factor or RF. And that's the thing that if we have some estimate of SXO, it gives us some idea about how much oil we can produce from the reservoir. So a greater SXO means that we can produce higher volume of oil from the reservoir. And in the case that SXO is equal to SW, which means that hydrocarbon is not movable and we are not able to produce any hydrocarbon from the reservoir. So that's the reason SXO is important as well. And how we can calculate SXO, again, it is similar to the first Archie's equation. Here is the second Archie's equation. And in order to do so, we need to calculate RMF, RXO, and if we have some estimate of phi, then we can estimate SXO. So just remember that the first Archie's equation was this equation, RW over RT over phi. As you see, these two equations are very interesting because they link some measurements of resistivity to hydrocarbon saturation or water saturation in the rock. And from the water saturation, we are able to have some idea about hydrocarbon saturation. So if we have some idea about the type of hydrocarbon that we have in the reservoir, for example, if we have gas in the reservoir, or if we have oil in the reservoir, then we can estimate the hydrocarbon saturation in the reservoir as well from these two equations. And not only we are able to estimate hydrocarbon saturation, but also we can estimate the volume of the oil and gas that we can produce from the reservoir. Okay, guys. I hope that you have enjoyed this lecture today. As you see, what I presented in this lecture, I just provide you with some important definitions that we have to know in order to assess the reservoir better. And what you're going to learn in this course, you're going to learn how we can estimate the porosity, how we can estimate these resistivities, RT, RW, RMF, and RXO, in order to accurately assess a reservoir. Thank you very much.